Good morning. So today is going to kind of be a conglomeration of different ideas, and we're going to start with a few things and end with a few different things, and a lot's going to be going on. So feel free to watch this video a couple times, maybe play it on half speed. I know I speak fairly quickly. Um, just feel free to get it done. I haven't assigned any homework problems yet, but we'll get there when we get there. So today's main focus is chapter 3.2, or section 3.2, I should say. And if you've already logged into Pearson, you should have access to the textbook, an ebook, and then you can go through and see all the things that I'm pulling my lectures from, worked out and with comments and more diagrams than what I can include in a presentation. So section 3.2 is all about the derivative as a function, which we'll get to what that means in a moment. But first of all, I want to start with what is a function? So maybe this is review for you, maybe this is a new way for you to think about what's going on, but what is a function? And a function, what we normally call f, is a rule that assigns each element x that lives in the domain to exactly one element f of x in the range. So here I have a cute little diagram that I've drawn myself, and it's a little black box or a little machine of sorts that it takes in some sort of input from X that goes into my machine. F does something to it. Maybe we know what's going on, maybe we don't know what's going on, and it gives us some sort of output, F of X. So I use the words domain and range, and what exactly does that mean? The domain is the collection of all of the values that we're allowed to put in. So all of the things that are fair game as far as input. So here I've got a little bubble and I've got A, B, and C in it, and maybe more things live in this bubble. Maybe it's only A, B, and C, who knows? And F maps them to F of A, F of B, F of C. And it maps them to the range. And the range is the collection of all of the values we get out of our function. So let's go to an example, and I think this is going to be a pretty useful example. Our friendly function f of x equals x squared. So the question is, what is the domain and range of the function f of x equals x squared? And you can go ahead and pause and go back maybe a slide and see for yourself what you think this might be, but we'll get to it in a moment. So welcome back from your pause. And the question is, what is the domain and range of the function f of x equals x squared? So our answer, it's very wordy, but that's okay. We'll walk through it together. F is a function, and it's defined for all values of x. Therefore, its domain is the set of all real numbers written negative infinity to positive infinity. And this just means I can put in whatever number I can think of. I can put in 15, I can put in negative 52, I can put in 3.5. Any of those numbers, as long as they're real numbers, I can find them on the number line, are fair game. I can plug them into x squared and I'm going to get a valid input, or I'm going to get a valid output. So our domain is all the real numbers from negative infinity to positive infinity. Because x squared will always give us a positive number, regardless of whatever x we put in, the range of our function includes 0 and goes all the way to positive infinity. So we can include 0 because if I use the number 0, well, x squared of 0 equals 0. So we get to include 0. But if I put in -1, well, -1 squared is +1 because a negative times a negative is a positive. So I'm only ever going to get positive values out. And this is to say, we can give our function f any number we can imagine, but we will only ever get a positive number out. So that's kind of what I'm thinking of when I'm saying domain and range. And I'm going to use these values or these definitions again and again and again when I come to talk about what we're doing with derivatives and limits and all that good stuff. So that was our brief interlude into functions. And now we're going to get to the derivative at a point and how we can represent it as a function. So our current definition for the derivative of a function f at a fixed point a is as follows. And it's really emphatic that we talk about this is just the limit at a fixed point a. It's the same as finding the slope of a line tangent to the curve f at a point a, comma f of a. And the question is, well, can we generalize our idea and consider all suitable points in the domain of f? Maybe f is our function x squared, in which case I can put in a particular value, but I know that I can choose from all of the real numbers. So what if we let a vary? That is, we let a take on any value we want. We can represent this idea by replacing a with the variable x and rewriting that first equation as the following. And this is f prime is a function. I give it something, it gives me something as an output. And this is the derivative of f, and it's a function. And it can be geometrically interpreted as the slope of the line tangent to the graph of f at a point x of f of x, where x can take on any value we want. So you can imagine a million tiny little slopes going and mapping all along a curve. So let's do an example. Find the derivative f of x equals negative x squared plus 6x. And I'll go ahead and let you guys pause and come back to me. So you've paused, you've come back, hopefully you've gotten far. If not, that's totally okay. So the question is, find the derivative of f of x equals negative x squared plus 6x. And we're going to begin with our limit definition of the derivative in terms of x, that equation 2 from a few slides ago. So f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So we're going to go ahead and substitute in. Right over here, we just substitute in f of x. And over here, we substitute in f of x plus h. So my x becomes x plus h quantity squared minus 6 times x plus h. Well, we can go ahead and expand that first term and then group likes terms, and we see that we've got a positive x squared and a negative x squared. We've got a positive 6x and a negative 6x. So when we cancel all of those out, we end up seeing that we're just left with negative 2x times h minus h squared plus 6h. Well, if every term's got an h in it, we can pull that out. I've got an h in my numerator and an h in my denominator. Those two will cancel out. And I'm left with the limit as h approaches 0 of negative 2x minus h plus 6. There's nothing more we can do except take the limit. And so we go ahead and do that. Our h term goes to 0, and we're left with negative 2x plus 6. So this tells us that for the graph, f of x equals negative x squared plus 6x, at any point, I can plug in some value a into this bottom equation and get out the value of the slope. So I'm getting negative 2 times a point x plus 6. And there's a pretty good graph in the book that explains a little bit more of what's going on there. So now let's talk about notation. I mentioned earlier that we're kind of just going all around and talking about a bunch of different things. And this is one of those moments where we're just talking about a bunch of different things. So we've talked about a difference between h and x minus a and x plus a and all that good stuff. But if I've got a point x1 and a point x2, the difference between those, or the change in them, is delta x. And this is going to be the capital Greek letter delta. So delta means the change in. So delta x means the change in x, and is computed as delta x equals x2 minus x1. And we can do the same thing for y. So instead of putting in y values, I'm labeling them f of x2 and f of x1. So delta y, the change in y, is f of x2 minus f of x1. And often the limit, f prime of x is written as the limit as delta x goes to 0 of delta y over delta x. And there's a couple more notations that we'll come up with that you'll see are frequently used when we're talking about differential calculus. But you can see as delta x goes to 0, so as the difference between x2 and x1 goes to 0, so as x2 approaches x1 or as x1 approaches x2, it doesn't really matter which way you go. You will get a different slope out because you're at different points in your graph, but the point is we're taking a limit. We know what we're doing. So more on the notation front. Often f prime is represented in many different ways, all of which you're going to become familiar with. So we have f prime of x, and that's the same thing as saying y prime of x. And that's the same thing as saying dy over dx. And maybe you've seen this notation before, but once we take the limit, we drop the delta notation, and mathematicians are lazy, so we just write a little lowercase d to represent delta. So dy dx equals df dx equals d dx of f of x. So all of these are the same way to express the exact same idea. It just depends on which one you like best. But if I ask you about dy dx, that's the same thing as asking you to find f prime of x. So let's go ahead and do an example. So let y equal square root of x, and I want you to compute dy dx. So if dy dx is the same thing as f prime of x, you can go ahead and use our definition for f prime of x, that limit of f of x plus h minus f of x all over h. So take a moment, pause, and see how far you can get with this example. Welcome back. So let y equal the square root of x and compute dy dx. So we begin with our definition. Dy dx is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So we can go ahead and plug x plus h into our function for this very first one, and we get the square root of x plus h minus just f of x, which is the square root of x, all over h. Now, there's not much we can do with this, so we're going to go ahead and multiply it by the conjugate of our numerator. And we want something on top equals the same thing on bottom, so when this divides out, it becomes 1, so we haven't broken any rules. So we multiply by square root of x plus h plus square root of h. So we change signs right there in the middle. All of that divided by square root of x plus h plus square root of x. Well, now this complex conjugate, or the conjugate on top, we multiply through and we end up with an h on top. Well, h divided by h, which means we're just going to be left with this denominator. So we've got 1 divided by x plus h plus square root of x. Now we can go ahead and take the limit as h goes to 0, and we're left with 2 copies of square root of x. So the f prime, or dy dx, or the derivative, or the slope of the line tangent to the graph y equals square root of x, is 1/2 times 1 over square root of x. So finally, here are a few laws, and you're wondering, well, we just got done talking about continuity, so why are we worrying about all of this sort of stuff? So let's talk about this for a moment. A function f is differentiable at a point A if f prime of A exists. It is differentiable on an open interval if it is differentiable at every point on this interval. That's just a definition. Go ahead, write that down, memorize it, all that good stuff. But finally, we get to a theorem. If f, our function, is differentiable at a point A, then f is continuous at that point A. However, the converse is not true. There are functions that are continuous but not differentiable. Think about the function absolute value of x. We can't differentiate it at 0, but it's still continuous there. So that's a good example. That's going to be it for this presentation. And actually, for today at least, that's going to be it for what I'm going to present to you. I'm actually going to link you to someone else's video, which I think does a really good job of explaining what the next concept is as a part of this section of the book. And that's going to be all. All right, I'll catch you later.